Right, then, well, welcome back.
Yeah, thank you. Welcome back. And today I hope to read the fruits of all the efforts. So the goal was map filtering for analysis. And so let's do it. So what is filtering? This is the filtering exact sequence. So what I want to do is, we have this fixed manifold M, which is smooth and oriented. And it's about the structure set of M, and I'm writing here the little close, of course, a little index M, because we have discussed it, but we can extend the long exact sequence all the way to the left to infinity by crossing with disks. And we have to think a little bit about what we do with the boundary, because after crossing with the disk, it's no longer closed manifold. That's all sorted out, and the methods would extend that way, and don't talk about it. Still, there is a long exact sequence, and we're really getting a map from this long exact sequence to the K-theory long exact sequence. So the structure set is probably what most people want to compute in surgery theory, and we know that it fits into this sequence where we have this normal set, which we also saw can be made into a group when one picks a base point, and the identity from M to N is a base point in here, so that's actually a group and a value of a homology theory on M. And the last thing which is coming up here is this F group, which I'm taking the liberty to, again, having discussed issues with base points, but to use the fact that only depending on the fundamental of M, as we saw. Maybe M is also connected. And, well, there's at least one term which is not part of this class, which is that there is an action on the L group on the structure set, and in the sense of, well, groups or pointed sets with action, this is an exact sequence. We'll discuss a little bit in the first talk. Okay, so this is this, and I'm going to talk about the cycles for that and the equivalence relation in a second, because that's what I want to do. I want to take a cycle, I want to map it to the corresponding class in the K-theory groups of the C-star algebras, which are our target. And this is the long exact sequence of this short exact sequence of C-star algebras, where we have a C-star M till the gamma we learned about last time, and D-star M till the gamma involved. So the structure set maps to Km plus 1 of D star of M till the gamma, which I call the structure algebra just because of that. That picks up the invariance of the structures. And this map, which I'm going to define, is going to be called rho. And now you know also where the other things are mapped to. This is mapped to, let me just abbreviate, K homology of M, which was incarnated as the M plus K theory of the quotient algebra. So that's of course what we map to, but it's a bit nicer to think of it as just mapping this homology theory to that homology theory. And the final thing is that we map L group to the K theory of, well, it's this C-star guy that also there we saw, it only depends on the fundamental group, which is really computed here as the Km of C-star into the gamma. So you see the pattern, this depends only on the group, this depends only on the group, this is a homology theory, this is a homology theory, these are structured. It's quite nice. And sure enough, this has to extend to the left with C star
structures is KM star M tilde and so on.
Well, it's a target for the structures. That's why I call it the analytic structure. And I'm not the first one to do that. Also, Rho and C just call it that way, but really because it's the target for the structures. Right? And here we have an action of this group on this set. This is a group homomorphism. Recall that in such a case, this acts on that just by taking something in here, positioning it forward and adding. So there is an evident action each time you have group homomorphism, which sends this little commute. So this map I'm calling APS index, and this map and to get this completely right, we will at some point have to invert 2 or divide by 2. So we really better should invert 2 throughout. Okay, that's the goal, and we have to define alpha beta in ups APS. Define rho alpha on cycles. Once we have done that, we're not yet done because we have to check that things are well defined. And this has to do with what is the equivalence relation in this. What are the equivalence relations in the search exact sequence? It's always some kind of bordism. Right? That's the idea. It's always a bordism, and of course you have to make a precise notion of it's bordism of everything you had in the cycles. You have to have in the bordism. That's the idea. So checking well defined this means we need bordism invariance of the suitable kind for whatever we construct. And the final thing you have to do is you have to check commutativity. And then I guess, I probably won't get to that, we should give some examples to show that I'm not just writing down zero maps, which would satisfy the first 3 things, but wouldn't give us so much, it would be so exciting, right? Okay, good. So, which one is nicest to do? Alpha. Yeah, once again, we need a cycle for the normal set. What would such a cycle be? Yeah, so, take. So, we decided that n is our m, and we would have then a second one, and I call it m2. And then F is a degree 1 normal map. That's the equivalence class of this is a cycle for the normal set. So our task is to define alpha, which is living in this D star not C star world. And of course we know very well how we can use the signature operator, having learned what we have learned, to make cycles in D star not C star once we have closed smooth manifolds as we have them here. So we have this is what I call fundamental class of the signature operator. Okay, there's one guy in for M2. We call it on the signature operator. This in a priori in Km of M2 as an abbreviation for this D star not C star stuff. And we saw how to do them, right? It's no problem. And there's another one we have in for M, living in K model of M. now we have two of those guys, but actually should get one thing and should live here. Now that's not so hard. If you remember that our C star and D star things were functorial, at least in K-theory. So there is also use for the map now, we haven't used yet. If you do push forward in this map, then we land here, then they're both in the same group. And if you remember that this is really something where we pick the base point, which is m should be set to 0, so you see the information from m should be subtracted to get the thing right. And that is what alpha of this thing is going to be. Okay? So, very nice.
Excuse me?
Yeah.
So do we lose all the information about the normal data completely?
Yes.
No.
You don't use it.
We use it, we have a map of manifold, that's it.
Yeah. So it's a bit disappointing. You see there's something on the way. Probably don't expect to have isomorphisms necessarily in all cases. At least that's a question which somehow is a deeper question than just an easy check of definitions. Depends on if it works on isomorphism conjectures which are hard to prove. Okay, so let me do row next. So there's still quite a bit to do, and this is on the blackboard. So let's first do the cycle definition of row. So for that, we should remember what a cycle for the structure set is. It's your turn. It's pretty much the same thing, only that F is then a homotopy equivalence, right? So copy that. Yeah. So it's now homotopy equivalence.
Can you also describe this explicitly in this? I mean, you have this isomorphism of the K groups here. Can you describe it explicitly in terms of Kn plus 1 and then this quotient alpha? Or?
What?
Alpha.
I showed you how to make a fundamental class out of a signature operator. That is my definition. So really you think of this here as what did we do? We said in the even dimensional case we have this signature operator, the signature. We can plug it into this function chi, which looks like that. That's going to be an odd operator. We can take the even part of it. We can multiply with the unitary, identifying the even with the odd part. That's an invertible element in E star mod C star, but completely invertible because there's a little problem with the zero spectrum and the chi not being equal to -1 and 1 completely. And we take its class. That was the definition of that guy prior to this. So it's completely in the world of index theory that I think of this definition. If you had another definition in mind, you would have to check that the two are the same. Okay? So
This is on M, not on the universal cover.
this is something to cover.
This is on, okay.
It turns out that if you go through the calculations, you might as well do it on M itself. I mean, that is not too hard to see that it gives the same equivalence class using this isomorphism between, we call that was D star M mod C star M or D star M tilde gamma mod C star M tilde gamma. We know explicitly how to identify them, and actually if you look at this construction you see this is compatible with either using the signature operator on M or on M tilde under this isomorphism you get to as the same side. So yeah. Okay, so what is the extra information we get from this? You see, the idea was something is defined in this class, in this group, and we should have better information, and then we can make a similar definition, and it should live in D star of M tilde without quotienting out. And what was this extra information? The extra information would have been that our operator is invertible, so it's very good that we wrote this down, because then this little error on checking that this squares to compose with this adjoint is equal to 1, so that this is an invertible element, would work without running out C star, as soon as we have an invertible operator here. and you can take a chi function which is just taking values -1 and +1 on the spectrum. So you would actually like to say, under this situation, the signature operator is invertible, because if it was, then the same construction would give us the improved element in the case here of B star, which is what we want. And that's actually exactly what's not happening on the nose, because the operator isn't changed. I mean, that this is a homotopy equivalence, it doesn't make the operator, force the operator's signature operator to be invertible. It's the same one we had before, but now comes deep under the input. Under input construction by using standardist, and maybe the invariant choice is proved by Charlotte Wahl. We know one thing about the signatures: they are homotopy invariant. So that should be reflected somehow. Right? What does it mean that they are homotopy invariant? It means that if you take this class and take the actual signature, the index, then we get, well, because of this difference construction, we get 0. Right? If we start with a homotopy equivalence. And now we expect that there should be a reason for that to the left, analytically. And this is happening, and this is this analytic input, namely, there is a perturbation in the sense of we take the signature operator on M, this time union M, and perturbing here just means we add some other operator, some small operator to it. This is an unbounded one, this is a bounded one, it will actually be in C star. Depending on the homotopy equivalence, so there's the data going in as it should. Here we go. So then you call this perturbation CF, such that this perturb operator is not, this is invertible. And this perturbation is unique up to homotopy, which means if we make constructions in K-theory, we will always get the same result, because K-theory is homotopy invariant. Let me show you how this looks like. So the idea of it is, what is the signature operator on the disjoint union of two manifolds? Well, we just have the forms on one manifold, we have the forms on the other manifold, and the forms altogether are the direct sum of these. And the signature operator on M, well, let's say M2, and the signature operator on M, they just preserve their own form spaces. And both of them might have a kernel, but homotopy invariance says the kernels are the same. So that we take the difference and get 0. And all you want to do is, but what is the kernel of the signature operator? That's the kernel of the Laplacian, that's just the cohomology, the round cohomology. Right? So, and what I want to do is I want to use the homotopy equivalence, I want to use it, what it's inducing on the, I want to do the pullback map, restricted to the kernel of the operator. Pullback map, yeah, that way is good. And here it's adjoint, which is equal to its inverse, which is pullback with the homotopy inverse. Right? The induced map on homology actually is invertible, and you have a well-defined inverse, it's just a pullback map by the homotopy inverse. And call that the round homology of the. So it maps isomorphically the round homology of M2 to the round homology of M1. And here we put just the pullback map, restricted to the kernel, adjoint, which is the pullback the other way around. And if you compute the square of this thing, you will see it is going to be an invertible operator. What previously was the kernel now is just killed by making this change between the two kernel maps, the two kernel spaces. Okay. So it's a kind of algebraic check to see that this new thing is invertible, provided the stuff really makes sense and we have 0 as an isolated point in the spectrum, analytic difficulties which come up here. And that's exactly what is not happening on our M tilde, and that's why this trick doesn't quite work, and we have to work hard to make this operator, but the basic idea is this one. And observe also that this is compatible with the decomposition of the form part into even part and odd part. The homotopy equivalent, which is orientation preserving, which it has to be in our cycles, preserves the even part and the odd part of the homology. Okay, so that is the idea. This makes this operator invertible, and now it's another fact such that our analysis still applies. So the operator is slightly different from the signature operator, but it has all the good properties we need so that we can carry out exactly the same program. And if the analysis still applies, we get, therefore, a class, so lift of the construction of the fundamental class gives first rho tilde of this homotopy equivalence, let me say. This would be as we saw it before. Let me sketch it, we do it. This is U composed with pi of this signature operator plus the perturbation. So, and now, because this is invertible here, the whole construction works without modding out C star, and we get something in the K theory of E star and gamma. It's like that. Now, we can and should use F once again to push forward to the K and S1. Just of E star of M tilde. Use F here and the identity here to push forward. And that is the official definition of the images definition of probability. Here we go. So we use all the ingredients of our K theory, index theory, and apply it to an invertible operator, and we end up in this structure. Analytic structure. So maybe we can check. So check of commutativity. We haven't checked that the maps are well defined, but we can, provided they are well defined, now already check that the diagram commutes. Why that? If we have such a M2 M homotopy equivalence, we assign to it this rho of F, which was defined as this U of the signature operator plus this perturbation. And this needed to be invertible to be sensibly defined in here rather. But if we map it further with the quotient map to the K theory of E star mod C star, we wouldn't need this to be invertible. The construction would work. So we can plug in a little homotopy by putting in T here. T is 1, this is just the construction we made before. If T is 0, it wouldn't work in the K theory of D star, but it still makes sense in D star mod C star because we don't worry about the invertibility, and we get just the construction of the index map we had before, of the fundamental class we got before. So we see that if we compose with this projection from D star to D star mod C star, this is the same as well, maybe I should also use the F to put the two things into E star of M, and that is really the same as the definition of alpha of this cycle. So built in that things commute. because we just make the definition for that thing.
Where's the minus sign?
Right. There's one detail to be done. I should really have to work here with the opposite orientation. Otherwise this won't work, and this construction will not be an operator, which it has to be. And if we take the signature operator of the manifold with the opposite orientation, its index for its fundamental class actually just negative of the one we had before. So that's why when you decompose this T0, it's just decomposing to two pieces. Was it here? But this one has an index which is a minus of the index it would have if this would not have the opposite orientation. Okay. So it works out fine, and if you do block sum, the indices just add. So this is sketch enough for that. It gives us an idea why this works. Okay, so now comes the last task. Need also APS index. For that, we need a cycle of L. And now let me write the M instead of the pi 1 of M, because we know that geometric cycles somehow see this space in the end. So how does a cycle for this group look like?
This letter rho, there's a different invariant in index here which is related to a fundamental group called rho. Is it an accident or is
No, this is indeed related. So that's why we call it like that. So we can recover, let's say for finite groups, the usual rho invariant from this map. That would be one of the non-trivial sample parts at the very end. And if you would use the maximal sister algebra, so you have to fiddle around a little bit, then you could do that for all fundamental groups. Here we have a little technical problem with our setup for the general case. But by and large, this is just contained in the row we like. Now, I answered your question, you should answer mine. What are the cycles for L? You forgot. Okay.
I mean,
so,
there's the geometric definition, the algebraic, I don't know, but the geometric one.
of course, I need the geometric one because I want to take these geometric cycles and apply indexes to them. So, the M, that is something one should remember, is just a reference space to which the cycles map. So, somehow we make that map to M. And the cycles themselves are, well, we have two kinds of them. There are some of those which are closed manifolds, but then there are more. We need the class to fill up this thing. We also have manifolds with boundaries somehow involved. So we have two manifolds with boundaries actually. And we have a degree 1 map between those. And on the boundaries, the restriction is the homotopy equivalence. So here it's the degree 1 normal map in the totally, but the restrictions to the boundary are homotopy equivalences. Now, I don't know, we have M1 and M1 prime, and F1, and M2, and prime, and F2. So that's a cycle. And we can work with those cycles, but let me remark one thing which is important in a short while. The pi-pi theorem, now that's an exercise to really implement this, gives something called wall realization. Two such cycles are equivalent if we find a Bordism of such things, which can change everything in the picture, whether at the boundaries with homotopy equivalences. Otherwise, it can change M1 prime and M1 and M2 prime and M2. They can all change during the equivalence. And indeed, whenever I have such an X, which is represented by something like that, in general, for each X and each Yeah, maybe you have a homotopy equivalence in mind, which you would like to see in such a cycle. Pick it. Maybe I'm not sure whether I really can completely generally. The M2 prime shouldn't be too arbitrary. Let's say M2 prime should be M, and the map down here is the identity. Okay? So if my wish is to make a cycle where the homotopy equivalence on the bottom, F2, okay, is a given one, and the map manifold here is the M for which we compute the group. There exists a representative. X is equal, but after all, X is an element in the group, so it has representatives. But we can make a very special one, namely one, as I indicated, where the bottom map is the given F. And even better, the right-hand side manifold is M times the interval. Okay. And this map here is the identity map, the projection map.
But M is smooth.
My M is smooth. I guess you can improve that, but I need it only for that case.
Before, originally the middle manifold was only the Poincaré complex.
No, in our cycles it's always, I don't know, maybe there are even more general cycles I can choose. But because of this realization theorem, we also know we can certainly stick to manifolds. Here we have some other thing, W. We don't know what M1 is up here. It comes with the F1, I guess, because of one equivalence, and this is the V1. Okay, so the theorem says whatever X is, whatever F is, we can make this representative which looks exactly like that. Okay? And this is a consequence of the pi-pi theorem and called Moore's realization theorem. Okay, so these are manifolds with boundary. First step, we want to define some index-defined row of such a situation. Okay? First step is we attach infinite half cylinders boundary of whatever we have times 0 infinity throughout. So a cycle looks then like constant part going out infinity, the W part, the constant part going the other way, then the map F, and restricted to the boundary plus the product structure, and it's this homotopy equivalence times the identity on the interval. Okay? And down here, so if we look at what we have done so far, it's sort of in between, right? We learned how to take manifolds and map between those and make these fundamental classes. We also learned how to make a slightly better thing if you have a manifold and a map between the two manifolds and map between those two, which is a homotopy equivalence. Right? In one case, we have the class living in D star not C star. In the other case, we have the class living in D star not 0. Right? Now it's in between, so expecting is, as I told you, we have this philosophy. Use the best algebras. Abstract C star, abstract D star possible. And that's the situation here. The little f at infinity being a homotopy equivalence implies we can improve C star by making it smaller. Something smaller. And we should do that, right? Each time we have extra geometric information, which allows us to make our construction. Recall the construction is always the same, this type here. Right? If things work out in a smaller algebra, if we have to model out less to get this well defined, we should take advantage of this situation. And so I want to do that here. And you see it's clearly in between having not to model anything and having just the full C star to model out. So we expect this is the intermediate thing between 0 and between the full C star of M to the gamma. I won't explain how that goes, given the time, but it is something about the fact that all our algebras and our constructions have a built-in sort of locality. Right? That's already visible in the algebras. The C star is consisting of operators which have finite propagation. There's some locality built in, which tells you that the homotopy equivalence only being given at plus infinity up there still should have some use and some meaning. And that's indeed what is happening. So just fact. So we find some kind of a partial acidic perturbation. And that's perturbation, which only makes it partially invertible, such that the signature operator. Now let me call this thing here W infinity attached to this half cylinders. And I guess I have two of those, so the whole thing put together is now my curly W infinity. So disjoint of those two, we change the orientation on one side as we did before, so we have one manifold to play with, and it has this infinity ends attached to it. Right? And there's a signature operator on this huge infinity, curly infinity manifold, rather it's covered with gamma coupling, and there is this partial smooth this perturbation, which makes it a bit more invertible than it should be in the first place. And let me just say that this construction we make to it using the chi function and this u, the same formula we had before, gives the class in something called P star of space, W infinity, gamma, that's A modulo C star. And now comes the subalgebra. It's consisting of both things which are concentrated on the core submanifold W, where it did not attach the infinite cylinders. I'm sitting somehow inside this thing where attached the infinite cylinder. Okay, so that's a new thing. And I should maybe quickly tell you what that is. Where C star of this smaller thing inside the bigger thing. And the gamma is consisting of, well, that's superficial because I really should write down the cycles which are strictly preserving, having all the finite conditions first and then take the closure. But we be precise, T's in C star. So these are operators on the full space, on the infinite attached space, but they're special. And they live in the C star gamma. Okay. They're special in the following sense. They really are supported at least near W, the core part. So what I want to say is that there is an R such that if you take phi living in the boundary times R infinity, so living somewhere out at infinity, and you apply t to it, you get 0.
So you mean that phi is supported there?
Yeah, phi is. And the same for the adjunct. Meaning the image of whatever you take and you plug into T lives on the complement of this R part, R up to infinity. So this is like if you think of an infinity by infinity matrix, where the infinity corresponds to going out to infinity in this attached cylinder, it's really living only in a finite part of it. All the rest is zero. Okay. So that's very nice.
So do you want it only on one end or on the other end?
Well, this infinity corresponds to the whole ends. So the whole boundary is top and bottom and left and right all together. Okay. So it's really, I should have thought, I mean, this is a construction you make for a manifold with a boundary. You attach a cylinder. Now the cylinder is easily drawn to go out in both directions, but bend it up and then look up into one direction. Yeah.
Does this perturbation CF really only depend on the homotopy equivalent small f and not on the whole map big F?
Indeed.
Okay.
What you would do, to describe this in slightly more technical terms, you just take the full cylinder, then you can make this perturbation on the full cylinder, and then use a partition of unity grafting in trick to use the same operator we had on the full cylinder and put it into this manifold, let it act on functions which are defined in this manifold by cutting off, applying, and then cutting off again, and so on. So this is a construction, and it depends, of course, only on what happens at the cylinder. So the little f. And the little f is, of course, the f on top and the f on bottom put together. So. Very good. Now, this time, I want to use the index map in theory, and so each time we have a class in such Schick quotient, we also have, by applying the boundary map of a long exact sequence corresponding to the short exact sequence, we have, one actually, a class in Kn of this guy. And now you might not be too surprised if you think of the description I gave. This is just like finite matrices getting bigger and bigger, that the K-theory of this is the same as the K-theory of the core part. Okay. It's the K-theory of the alpha of 5 by 5 matrices is the same as the K-theory of the 8 by 8 matrices, is the same as the K-theory of the finite matrices inside infinite matrices. The same principle applies here and tells you in the end we don't get an index exactly where we want to get it, namely, well, almost exactly where we want to get it. Finally, you can use the f we haven't used yet to push further to the right hand side, and then use the map all the way to m to get the index in m. I should do that. Once again. So if we take this, we want to map it to, once again, we can construct a class in the Kn of C star of double tilde gamma, which is just the union of this and this with the inverted orientation here. And then we can use the functoriality for this map here, or the composition of those two. How's this called? Gamma star, and of course the X star as well. So we really have this map which sends everything to M, and we can use the functoriality to get finally to the K, the C star algebra of M. And this image, so we have this class defined here. You can see it up there. Okay. Coming from the construction, using the fact that it worked modulo this little C star algebra, and then taking the boundary map of the long sequence, we can map it further, and what we get is what we call the APS index of this cycle X. And why is it called APS index? Because it has something to do with the index or the signature operator on the manifold with boundary. Also, we got rid of the boundary attaching the infinite cylinders. So that's the standard trick, which is done in APS as well. So, no big surprise. Very good. let me.
Why did we expect to find such a perturbation, given that the map, the capital map, was not a homotopy equivalence?
We didn't find such a perturbation. The capital F is not a homotopy equivalence, that's true. But the definition of the cycle in L theory is that the boundary maps are homotopy equivalences, to start with.
Right, but I mean the D depends on the entire manifold, including the constant.
D of W,
Yeah,
D of W mod C on the core part.
Ah, yeah.
So really the idea is we
Yeah,
have
sure.
a problem on the core part,
This is
on the
right.
W,
Yeah.
so we have to mod out the C star, the operators which live on the core part, because there we have no control. But we don't have to mod out the full C star of the infinite cylinder thing, because outside we do have control. So let's check the next commutativity.
So it looks like all the maps now exist without inverting 2.
Yeah.
For you?
Well, we still haven't checked the volume invariance. That makes life harder if you want to do it analytically. Nonetheless, with enough work, you actually can check that the maps are defined without inverting 2. But the commutativity of the action boundary thing will only work if you divide one of the signatures by 2, which you can only do if you invert 2. So the maps can, for each single degree, if I'm not mistaken, really be defined without inverting 2, but you cannot make the whole diagram, without inverting 2. Okay, next thing would be commutativity. And the next place where it makes sense, which was we had normal maps, and we have the map to the structure set. And we should understand why our construction is okay. Great. So we should remember how we made out of a degree 1 normal map between some other guy and M, a class representing something in L theory. Do you remember?
How we did that?
Yeah.
No, I actually don't. I mean, in the algebraic, sure, but in the geometrical.
In the
Geometry
geometry
is
one,
tautological, but
it's tautological.
but I don't remember how it's tautological.
Again,
Do we take cylinders from both points and then
We take this map. So this are supposed to be manifolds with boundary with some reference
Oh, yeah,
to
yeah,
empty.
yes.
The boundary is allowed to be empty. That is also a manifold with boundary. So these are manifolds with empty boundary. The F has to be the V1 normal map, which is not homotopy equivalent at the boundary. Now the empty set here is homotopy equivalent to the empty set there. That's fine. So perfectly okay, and this reference map. Yeah. So this certainly. I mean, that's an easy map, topological one, you pick it up. And now let's see what our construction tells us to do. It tells us to take an APS index of a manifold, but we go here, which actually hasn't any boundaries. And in that case, if you go through what we did, this is just the usual index of this situation. Now, what we did here was we sent this in K-theory to the fundamental class. Right? And so we just discussed that here we send it to the index of the signature operator. And again, this is there's a difference happening because we have put the proper orientation on that one and then we push forward everything. Okay. And that was literally the K-theory of C star. And this map here
should be D1C.
This map here is by definition the index map, and the index is by definition the image of the fundamental class on the index map. So you see again by definition not much to be done. That's the advantage of this approach. Being at it, let me try to explain the commutativity of the last map. Now all maps are defined, so we can check all commutativities. You have checked 2 out of the 3. Let's check the third, and then see a little bit what we have to say about the defined map. Yeah, that requires, so the last commutativity, that requires to understand if you are in Lm+1 of our manifold M, how it acts in the first place on the structure set. Before we check that something is compatible, that this action is involved, we're good to know how this action goes. So our task is to take the cycle here, which is an M2, with a manifold M, and we call that homotopy equivalence, because we're in the structure set. And our task is to take an element from here, and we call it X, and then to define a new element in the structure set, which we call X plus this cycle, or X times this cycle. Okay. So we have to guess the construction already, but you clearly will agree that it's most likely easier to describe this construction in geometric terms if the X is somehow adapted to this guy on this side. So there is our pi-pi theorem we can use for exactly this purpose, which tells us better take the X represented by something which involves the homotopy equivalent of one structure. Now, what more we can put this. So this is this realization theorem. Here we have just some W, and it ends with some M1, I call it, fortunately, and with some other homotopy F1. Who wants to guess what the result of letting X act on this might be? Some manifold with a homotopy to M.
M1, F1.
Great. So X times M2 and is defined to be M1, F1. So maybe something else to be taken home. If you want to work geometrically, this is how the action goes. It involves a non-trivial step, because if your cycle X had been given to you in a different way, you really have to make it using the realization into this form before you don't know before that you don't know how to act.
But is it unique?
Huh?
Is it uniquely determined?
It's well defined. I mean, there are of course many cycles you get that way, but now you have to think of what the equivalence relation was. It was Bordism throughout, and you can see that the data of these Bordisms on the L side give you the Bordism for the S side of the top part. So it is indeed well defined, more or less by the way we defined our equivalence relation.
So, but this realization, in order to use it, you have to use some uniqueness of this realization. You don't, a priori, you don't know that.
Well, I just want to explain. Of course, this guy is not unique, but we know what the equivalence relation is.
Up to H coordinates. That's precisely the relation to this factor set.
So I don't want to discuss why it's well defined. You have to check it. It's something to be proved, but it's not too hard from the cycle description we have of all the groups involved or the sets involved. Okay, and now let's we also check what we should have So we need for commutativity, we need right to this we assigned an APS index, and let me call this thing again this W with F, the Western Union of the 2 and so on, right? So to this we assign this APS index using the homotopy terms at the boundary, and to this guy and this guy we assign these row invariants. Okay? And so what we should have is that if you take this APS index, which lives in the K theory of C star, if we push it forward to D star, it should be the same. I mean, if we add to this the row class of this, the thing we started with, I sort of started in the end. Very good. Why not? Which lives in the K theory of E star as well. We should get the row class of the other thing. That was, once again, how you define the action on the level of having one group mapping to another group. You take the image of one thing, we add, we should get the other thing. Okay, or, can we write that, I guess, out here, track here. And if I reverse the orientations, all the time the indices are replaced by negatives, so I can reverse the orientation throughout, and I get plus here. And that is row of the boundary of W. The F map, which is defined in the boundary of W anyway. Okay, so you see that the compatibility action with the maps comes down to a certain index theorem. If you take the APS index, forget a bit of information about it by pushing from D star to D star, then this should be raked off from the row invariant of the boundary. Okay. So commutativity at this last place is the same as this kind of index theorem for the APS index. And if you know the APS index theorem, it actually tells you something about the APS index. Can be computed with something which we forget because we push forward, and some boundary terms which are eta invariants. Eta and rho are two Greek letters, so indeed this is very much like the APS index theorem. We forget interior information. Okay? And that is actually a theorem. And myself, and she also have a version of it. We were only dealing with half the dimensions, and we have to make one extra correction here, and this is where we have to invert 2. This is really, we prove this more abstractly, not for the signature operator, but for general Dirac type operators. Notice related is the operator on the interior and the corresponding operator on the boundary. Now there is a defect the signature operator has, which is that if this thing is even dimensional, the boundary operator of the signature operator is actually the direct sum of 2 copies of the signature operator of the boundary. There is this annoying factor of 2 business going on, so that really what we prove here is not this theorem, because we want to apply to the signature operator here. We pick out this factor of 2 if we start with W being even dimensional. Okay? So this is, let me call it dm, and this dm is sometimes 1, and we are perfectly happy. And what was the m here? M, I hope, so let me say, dimension of W congruent to 1 or 2, everything is fine, but if the dimension of W is even, nothing is fine, we get this factor of 2. And so to get the thing really well defined, you better would divide the APS index thing on Lm plus 1 by 2, because then it's right. But to do that, so the definition I made was okay for Lm, but for Lm plus 1, we have to divide by 2 in half the cases. And if you go further to left, to make things okay, you have to divide by the same factor of 2, and then at some point, going 6 steps to the right, you have to divide by 4, and then we have to divide by 8, and so on. So it makes perfect sense. We have to adjust the definition a tiny bit, but we better work with the group where 2 is inverted. For that reason. Okay. And let me just finish. Well-definedness corresponds to Boolean invariance. And let me say this is standard for index, even if it's an APS index, and for fundamental class. So these were two of the constructions we're using. It's kind of a standard thing, particularly for the fundamental class, you really can find it in the literature. You believe that my definition is even others use. And it follows from this APS-like index theorem for rho. It is just above. So we would like to say that sometimes rows are the same. We have a Bourdism. Now these Bourdisms would then be Bourdisms where we have homotopy equivalence throughout. And that would mean that the index we define is actually vanishing. If you have homotopy equivalence, the index should be not 0 of a difference of two signature operators, one on the manifold, one on the homotopy equivalent partner. So this side would vanish. You would get that the row invariants of the boundaries are the same, which is the required Bourdism invariance for the row invariant. So time is up. I don't think we talk about the non-trivial examples, but let me just mumble the row invariants defined in APS. Something are contained in that picture, so it is not the trivial map of.
Is there a natural definition of the assembly map in the K-theory exact sequence?
Yes. So that's the two theorem, I guess. But I think I wanted to tell you last time I forgot. The fact is that what did we see? We saw that Km plus 1 of E star on C star. That was the K homology of M with these identifications using particularity, and we saw the Km index map of C star of M tilde gamma, which we identified with the K theory of C star reduced of phi 1 of M. Now, this is a manifold with fundamental gamma, so it has a homology map to Kn of P gamma, and punctuality is well enough. Indeed, the map we wrote down here factors through that. But so this was one thing. What am I saying? No, this is our map, which we defined, and there is another map from here to here, which is coming by using the punctuality of K homology, and then using the Baum-Kohn assembly map, which is a certain map from the K homology of the classifying space of a group, to the K-theory of the reduced C-star of the group. And it turns out that this diagram completes. So the index map is the Baum-Conn assembly map. That has been checked by John Rowe in some paper. Of course, everybody guessed it anyway. Depending on your point of view, you might say this is clear, or you might want to say have to prove something. It's definitely true. The index map is the Baum-Conn assembly map. So now there is a more sophisticated Baum-Conn assembly map, which you should use for groups which are not torsion free, and you should rather use some equivalent K homology of a certain space called E underbar gamma, and the better version of the Baum-Conn assembly map would be this guy here. And this is a canonical map like that. So the less good Baum-Conn assembly map here factors for non-torsion free groups like that, and that's a better version. And the Baum-Conn isomorphism conjecture, the isomorphism conjecture in topological K-theory of C-star algebras, says that this map is an isomorphism. This map is not always an isomorphism. If the group is torsion free, it is. Therefore, the less sophisticated map is an isomorphism conjecturally for torsion free groups. You might know. But it's certainly not for non-torsion free groups. So we do get a map which we can call the Baum-Conn assembly map in our picture, but in particular if gamma is not torsion free, this is not saying that in our diagram we have an isomorphism for one of the three arrows, and therefore the group in the middle which interpolates would always be zero, which would be the K theory of D star, which would be the structure K theory. So it's not true because of these discussions, despite the fact that Baum-Conn is included in our picture, that this K theory of D star, this structure thing, would always be trivial conjecture. So, yeah. Long answer to a short question.
If M is aspherical, can you sometimes see that this D star is trivial K theories?
So the most efficient way to do this is to use this argument and rely on others' work, which proved the Baum-Conn assembly map, the Baum-Conn isomorphism. But there are indeed tools to compute the K theory of this D star. You can apply Meyer-Vittorius arguments. So it's a little bit with some care like homology theory. There are some ways to compute it. Meyer-Vittorius among those. So for very special groups, you can use this trick to do a full computation of the K theory of D star. One example which comes to mind is the integers. And it indeed vanishes.
And that's independent.
That's independent of checking Baum-Conn differently. You can prove Baum-Conn using this method, but I think it's more difficult to use this method than most others which are available. So you can make your life hard, try to check it that way, but you might succeed.
I have a question. Well, somewhat of a historical nature. I mean, Eaton and Rowe came up with this map from the pseudo-exact sequence, so that predates the index theorem you just proposed to use for this. So how did they get about? I guess they define their maps differently.
They define their maps differently.
How?
They use so we always restrict to smooth manifolds, and you could go on to work with Lipschitz manifolds, as I told you in the first lecture. They also used singular spaces, congruality spaces, and they used not the signature operator, but rather the chain complexes one has there to make all the definitions, and then they prove for this more complicated world of more complicated spaces the relevant Boltzmann invariant theorems, for instance, and that way, and the homotopy invariance theorems, and that way, using more singular spaces, relying a lot more on chain complex methods, chain complex calculations. It's sort of a certainly related but different approach, and well, the problems appear at slightly different places. So it really can't be used, as far as I can tell, to immediately transfer the proof of this theorem to something which is done in X by X and row. But it might be possible to do. I don't know. What do you think?
I don't know.
You don't know.
All right, further questions?